Today I want to talk about the hockey stick identity, which is a common identity that's used in combinatorics problems, and it's basically an extension of Pascal's identity. So I've written it out here. If we start with R choose R, and then continue adding terms, choose terms, so R plus 1, choose R plus 2, choose R, until some finite limit k, R plus k, choose R, that's equal to R plus k plus 1, choose R plus 1. So just to get an understanding of what that looks like, let's say R choose R is 4 choose 4. We're going to have 5 choose 4 plus 6 choose 4 until, let's stop at 10 choose 4. This is going to be equal to 10 plus 1, choose 4 plus 1. To get an understanding of why this is true, we're going to take a look at Pascal's triangle, which, like I said, the hockey stick identity is just an extension of Pascal's identity. So let's start by let's make R1 this time. So we'll start at 1 choose 1, and let's go all the way until 5 choose 1. So that means k is 4, and all of these terms are going to sum to 5 plus 1, choose 1 plus 1, which is 6 choose 2. And you can see the shape this makes kind of looks like a hockey stick, which is why it's called the hockey stick identity. Now, at first it might not be obvious why this is true, but like I said earlier, this is an extension of Pascal's identity, and we're going to use it to prove the hockey stick identity. Let's consider 6 choose 2. 6 choose 2 is just 5 choose 1 plus 5 choose 2. And I'm going to highlight that a different color, green. Now, you can apply the same logic to 5 choose 2. 5 choose 2 is just the same as 4 choose 1 plus 4 choose 2. And 4 choose 2 is the same as 3 choose 1 plus 3 choose 2. 3 choose 2 is the same as 2 choose 1 plus 2 choose 2. And 2 choose 2 is just equal to 1 choose 1. And you can see we've completed the chain here. Everything is equal, and the hockey stick identity works. So now that we know why the hockey stick identity works, we can use it to solve problems. Let's consider this one from the 2015 AIME. Consider all 1,000 element subsets of the set of natural numbers between 1 and 2015, and from each subset, choose the least element. The arithmetic mean of all of these least elements is p over q, where p and q are relatively prime positive integers. Find p plus q. So let's start with the 1,000 element subsets of this big set. They're going to be 2015, choose 1,000 of those, right? We're just asking how many ways to make 1,000 subsets of 2015. So that's going to be the denominator of our arithmetic mean. Now we want to find the numerator. The numerator is just going to be the sum of all the least elements of these 1,000 element subsets. And to think about that sum, we're going to think about how many times each of those least elements ought to appear. Let's say we want to consider how many times 1 is the least element of all of these subsets. Well, 1 is going to be the least element of all of those subsets when the other 999 numbers are in the 2014 numbers that are greater than 1, so between 2 and 2015. So 1 times 2014 choose 999 is going to be, so 2014 choose 999 is going to be the number of times that 1 appears as the least element. And then we can apply the same logic for 2. 2 is going to be the least element when all the numbers in the subsets that it's in are greater than 2. So that's the numbers between 3 and 2015. So that's 2013, choose 999. And this is going to continue until we reach 2015 minus 999 times. So that's going to appear 999, choose 999 times, right? And let's just write 2015 minus 999 is 1016. So here we can apply the hockey stick identity. You can see it's kind of written backwards. We have the 999 on this side, but it's still going to work. So let's think about what the largest sort of hockey stick sum that we can take is. That's 999, choose 999, until 2014, choose 999, and that adds to 2015, choose 1000. And now that we've removed this, we've subtracted 1 from each of these occurrences. So this is going to disappear, this is going to be 1, and this is going to be 1015. Everything else is going to have 1 subtracted from it. And now you'll notice that because this term is gone, this is 1, this is now 1015, we can apply hockey stick again, except the largest hockey stick sum that we have is going to be 2014, choose 1000. And actually, we can keep going like this until we get to 1000, choose 1000. And actually, there's a ... between there for all the numbers in between. And this again is the hockey stick identity. And when we add them all together, this is the largest number in it. So it's going to be 2016, choose 1001. That is our numerator. You can just use the factorial definition to get that this is 2016 over 1001, which simplifies nicely to 288 over 143, and P plus Q is 431. And we're done.